Okay. Good afternoon, everyone, and welcome to the session. And in this talk, I want to introduce our effort for migrating the Hive workload to Spark, and our effort to the slides. Sorry, excuse me. Zhan. Thank you. I want to cover our effort to migrate the Hive workload to Spark and what's the challenge we hit and how do we solve it to narrow down the gap between the Hive and the Spark. First, I introduce myself. My name is Zhang, software engineer in Facebook. And Zhan, Wang is my colleague, and we collaborate on this project in the Spark Big Compute team. Actually, in 1.5 years ago, we initiated this project to do the Hive to Spark migration. And why we want to do this is to make the big. Yes, first I've got the overview of my topic. The first one is the effort. Next is our effort to narrow down the feature gap. Then we will go through the performance and the reliability improvement for Spark in production. The last one, we introduce some advanced optimization for extremely large job. Why we want to make the migration work? There are two major reasons. One is in Facebook, Hive is one of the major batch compute engine, and the workload actually double or triple every year. It's a big resource, one of the biggest cluster in our Facebook. We want to reduce the resource usage. And Spark as a more advanced computation engine, and the performance-wise is much better. Also, it gives the user more flexibility to write their own application logic. To save the resource is the basic initiative to do the migration. The second one is if we want to switch to the more advanced computation engine, for example, Spark or Presto, we want the data engineer, they don't need to learn a lot of new stuff. They can write the pipeline in the old way, for example, Hive. Then we want to identify and improve the feature gap between the Hive and the Spark. Initially, as the first step, we want to find how compatible between the Hive and Spark. We do the syntax analysis. As we find about 50% of Hive workload can migrate to Spark without any change. But this number is not high. We further look into it. We find if the top 10 feature gap, we can fix those top 10 feature gap, actually the compatibility can be improved to about 90%. This number is very good and encouraging because we only fix maybe 10 feature gap, we got a good cover. In Facebook, we have a lot of table. Actually, it has maybe hundreds of columns because the data is huge. And when the data engineer writes their data pipeline, we don't want to specify each column. Typically, in production, we find a lot of SQL is written like this. Select all the column except some column. But in Spark, we don't have this feature support. If we want to migrate this workload from the Hive to Spark, either we have to rewrite the SQL to specify every column. This is impossible because we have so many legacy pipelines. The second one is we added the feature support for the regex column specification. My colleague Wang implemented this feature, and also this code already committed to the upstream. The second one is the local file system writes. When the data engineer writing their pipeline, they want to do maybe some testing or some inspection of the data. So this in production maybe not used a lot, but during the development is used a lot. So we also implemented this feature and committed to upstream. The other major challenging one is the UDF support. We have so many proprietary UDFs. Because the Hive and Spark, there is some architecture level difference. Those, most of UDF may be supported well, but it does have some UDF. For example, we have the UDF, UDTF, and UDF Java function. Those function is similar to the Lambda function. The user can write arbitrary Java code inside of the UDF. We find in our production, actually, sometimes it has hundreds, even thousands Java code. It may be not a good engineering practice, but we have so many engineers, we have to support this feature. But in Spark, it has a driver and an executor. Those UDF, part of it is evaluated on the driver side. We have to serialize and deserialize to the executor side. During this process, we hit a lot of issues. For example, mainly the serialization issue. Those fixes are straightforward, but to identify the root cause is very difficult. The fix itself maybe just change some field to the transient field. But we have so many UDF. We pick up the major one, is very popular in some namespace usage. After fixing those major feature gaps, we improve our compatibility from a little bit more than 50% to 85%. But there is still about 14% those jobs cannot migrate to Spark directly. But for those 13%, there's some false positive. For example, there may be sequentially some pipeline. The first pipeline writes some table to the temporary, writes some data to the temporary table, then the following pipeline use those temporary table. When we do the offline scheduling, those table is not available, causing those table missing syntax failure. If you want to see our migration framework, probably you can take a look at my last year's presentation that has all the detail for the migration framework. With those improvements, we got a very good progress for our workload migration. In half year, our workload in Spark grows 3x. Here, the red line is the reservation CPU, and the blue line is the CPU. The reserve CPU here, the concept is when the Spark job requests the resource from the underlying resource manager, for example, the Zhang for the open source. They request this resource, but it may not run any task on those node manager because maybe it's blocking on I/O, or it's because the scheduling overhead on the driver. But this resource cannot be used by any other job. It's got wasted. The second one is the CPU usage. This is the real resource usage running that is running on the task. You can see the gap between the blue line and the red line is actually very big. Sometimes it's about 1.5 to 1.6 multiplier. Most of them actually is the blocking I/O. With those feature gap improvement, next, when we run those pipelines, the major initiative is to get the good performance in Spark. But the reality is sometimes it's not like that. Especially for join. Actually, for the small job, the job may be okay, but in our workload, the join sometimes the data size is very big. We have 3 major join strategies. One is the broadcast join, ShuffledHashJoin, and the last one is the sort merge join. In the broadcast join, typically, for example, A join B. If we assume B is very small and we can fit it into memory, the best way is build the hash map, broadcast the table B on every executor, then build the hash map for the table B. Then on the table A, we stream in the table A, then do the matchup for each row on the hash map, then emit the matching result. In this case, we don't have the shuffle. Also, we don't have the sorting. It's very efficient. In the ShuffledHashJoin, in the similar case, we have the A and the B, A join B. B is small, but it's not small enough to fit into the memory. Each split, when we do the join, we have the partition B. Each partition of B is small enough, can fit into memory. In this case, the reducer, after it fetching each partition, then build the hash map on each partition of B. Then do the match and the hashing lookup on each row of table A, then emit the results. In this case, we have the shuffle, but we don't need the sort. The third one is the sort merge join. In this case, both A and B is big. Even each partition, they cannot fit into memory. We have to do the shuffling, then the sorting. It's very straightforward. This is the most heavy one. So comparing these three cases, broadcast is most efficient. ShuffledHashJoin in the middle, but the problem is for broadcast join and the ShuffledHashJoin, they are not reliable, especially when the data estimation is not correct. In the runtime, we may hit the out-of-memory issue. In Spark, the out-of-memory issue, especially for broadcast join and ShuffledHashJoin, is not recoverable. If we have the data, most of the days, the data we can use the hash join, but someday, the same pipeline, the data may be big in some day. In 10 days, 90 days, we can use the hash join, but only one day, that big data is big. We cannot use the hash join because the out-of-memory issue. In production, this is very serious. We would rather choose the reliability instead of the performance. But when we choose the reliability, we don't have those optimization. So we implement a new operator, is a dynamic join. In this dynamic join, based on the stats to choose the join strategy. For example, if we choose the hash join, but when we do the in the runtime, when we build the hash map on the partition of each partition of table A, sometimes if the data cannot fit into memory, regular cases the job will fail. But here we catch the out-of-memory exception. Here the out-of-memory is the is the Spark memory management out-of-memory. It's not JVM. JVM is not recoverable. If we hit the Spark out-of-memory, we reconstruct the iterator, then do the regular sort merge join. The actual overhead here we say is if we fall back to the sort merge join, the hashing build-up phase is got wasted. But it improves our reliability in our production. With this fallback mechanism, actually we can leverage more aggressively with the ShuffledHashJoin. Here is the physical plan for our dynamic join operator. In the middle is a dynamic join. You can think it's about the combination of the ShuffledHashJoin and the sort merge join. It's a fallback mechanism. The other case is the bucket join. In the bucket join, on the left side, A join B. Typically, we have the same number of buckets. Then each bucket join with each other. Then we don't have the shuffle. Also, we don't have the sort. It's a very efficient one and used a lot in our production. But actually, my colleague teachers did a lot of work on this part. On the right side, here we also have A join B. But A and B have different number of buckets. A have 4 buckets, B have 2 buckets. Typically, in Hive, if the number of buckets of A is multiply of the buckets of B, Actually, we don't need the shuffle. In Spark, we also implement this feature. On the right side, we combine bucket 1 and bucket 3 in table A, then join with bucket 1 in table B. So we skip the shuffle case. Because we also use the hash join a lot. We leverage hash join a lot. So we also don't need the sorting for this case. And before we have this feature, we have to do shuffling. The real production workload actually running similar or even worse in Spark. But after this feature implemented, we see 2x or 3x improvement over Hive. It's one of the major workloads in our production. The next phase is when we do the migration, for small job, probably we can't have the fixed configuration. But for extremely large job, here is the example. We have 10,000 mapper, 10,000 reducer. It's a two-phase job. It's much simpler than our real production job. In production job, for those large jobs, we may have multiple stages. Each stage may have tons of thousands of tasks. Then we have hit a lot of issues. The first one is the IOPS. We use the HDD disk. It has the mechanical, we have to move the head. If we read and write a very small amount of data, the IOPS itself is the bottleneck. As I mentioned before, in the reserved CPU and the real CPU, we have a gap. It's about 1.5. The major gap of those is because the blocking I/O. So IOPS in extremely large job we see is about sometimes it is about 40%, even 50%. That's the extreme case. But anyway, it's one of the major bottleneck for our production. Also, in this job, we have 10,000 reducers. Each reducer have each reducer generates one HDFS file. We will generate 10,000 files. Actually, it's an overhead for the name node. Also, we have 20,000 tasks in this simple job. The scheduler also have a big overhead on the driver side. For this extremely large job, we have to tune it one by one. Especially, it will be very difficult if there's a data skewness. This is one of our experimental work to implement a new algorithm is a secondary partitioning. I simplify the case. The left side is the regular Spark one. Map and reducer, both of them have 6 times 6. The IOPS is 36. Also, the resulting file is 6. On the right side, we change it to 6 times 2. We have the 6 mapper, but 2 reducer. But when this reducer fetching the data from upstream, we further do the secondary partitioning, split them into 3 sub-buckets. So because the local split is a continuous read and write, the IOPS actually on the secondary partitioning phase is negligible comparing to the job itself. So it's about 12 IOPS. It's 3 times less. Also on the right side, we only have 2 reducer. It generates 2 files. But for the task execution granularity-wise, actually, because it has 3 buckets, those 3 buckets is joined one by one. So the size is the right side case is the same as the left side. It's 6 times 6. On the reducer side, we have this big task. Each big task, we have 3 small tasks. On the scheduler side, it only say 2 reducer tasks, but on the execution side, we do some tricky stuff to split those major tasks to small tasks. This is the second partitioning. Also, I want to mention that when the reducer fetching the data, doing the secondary partitioning is spilled to the disk. During this phase, we can calculate exact data size and how many records in each bucket. Instead of estimate the data size, we do accurate data size calculation. It has some pros and cons for this secondary partitioning. First, we reduce the IOPS. If the sub-bucket is 3, it reduce the size 3 times. If it's 10, reduce 10 times. The second one is the HDFS file. Reduce the HDFS file with the same factor. Also, we do the spill, we have the accurate data size estimation. We can do the runtime optimization as well. We also have the backward compatibility. If the sub-bucket number is 1, it has the exact same behavior as the original Spark. For this job, extremely large job, we don't need to do a lot of tuning. Typically, we say 500 partition, 13 buckets is good enough to have both CPU usage and latency. But the drawback is the parallelism is reduced. It has the original one has 6 reducers, but now we have 2 reducers. Each 2 reducers have 3 tasks sequentially executed. In production, typically our workload is waiting for tasks. It's not a big issue for us. The second case drawback is the reducer have to fetch all the data, then spill to the disk before do the computation. But for large job, our bottleneck is IOPS. This reduces IOPS with a big factor. So in our big job, we say both the good performance, both with the CPU and the latency. But for small job, we don't need this. But for extremely large job, actually, this is, in practice, we see a very good optimization. With those runtime optimization stats, when we spill the data to the disk, we get the accurate data size. Then now we do the join. We don't based on the estimation. We based on the accurate data size. A and A join B. We know exactly A small or B small. We pick up the small side. Then we know exactly each bucket, the size of the bucket. We know whether we can use the hash join on those buckets. Then we do the hash join or sort merge join. This behavior is determined at the runtime instead of the compilation time. In the meantime, for the regular Spark job, we decided the hash join or shuffle or the sort merge join on the job level. But for this case, we decided the join strategy on each split level. If we have one table have 10 partitions, if 9 partition is small, only 1 partition is large. Those 9 partitions will use the hash join. The 1 partition will use the sort merge join. This right side is flow. It's a little different from the implementation. First we pick up the table with a smaller size, then build the hash table on the smaller side, then do the hash join. Also, we have a catch-all case. Even with the accurate data estimation, if it hit the out-of-memory issue, we still can fall back to the sort merge join. Yeah, this is some work we push to upstream. By the way, for the secondary partitioning, it's our experimentation work, still not in production yet. Yeah. I would take this chance to thank for the big compute team, and especially my intern Wang and my colleague TJS. Thanks for their contribution. Yeah. Any question?